Welcome. May I have your attention, please? Okay, so for our Bellwork today, we're going to be multiplying polynomials together as a setup, an anticipatory set for today's content objective. We're going to be factoring, which is undoing multiplication of polynomials. We're going to factor polynomials. Let's go ahead and get started. So we know when we multiply two polynomials together, we'll go ahead and take each term in the first polynomial and multiply it through each term in the second polynomial. We can think of this as the double distributive property. If we have a binomial as my first polynomial, we'll go ahead and focus in on that first term in the first binomial x, and we'll distribute it through the second polynomial term by term using multiplication. So x times x is x squared plus x times 5 is 5x. And now we kind of used up that first term, that x in the first polynomial. Now let's focus in on that second term in the first binomial, that 4. We're going to distribute that through the second polynomial, term by term using multiplication. So 4 times x is plus 4x. And then plus 4 times 5 is plus 20. So we can see our blue product all the way through. We can see our green product all the way through. And now we'll go ahead and write our answer in standard form. We're not going to box this. We want to combine any like terms. And so we know we can combine like terms if the variable component matches exactly. What's a pair of like terms in this expression? Heather? 5x and 4x, awesome. So my final answer would be rewritten in standard form, highest exponent term first, x squared plus 9x plus 20. Raise your hand if you already had that, please. So who already had that? Woohoo! Great. So we'll go a little bit quicker. On the next ones then, we see the pattern. So we'll go the first term all the way through. We're going to go ahead and do x times x is x squared. And then x times -1 is minus x. And then we'll focus in on the blue -3. -3 times x is minus 3x. -3 times -1 is plus 3. And again, we'll combine like terms. Negative x minus 3x makes my final answer x squared minus 4x plus 3. And raise your hand if you had number 2 already. Number 2 already? Awesome, good. Thanks, hands down. We'll continue this party. And so now we've got x times x is x squared. And then x times -2 is minus 2x. And then we've got plus 7 times x is plus 7x. And then we got plus 7 times -2 is minus 14. Again, like terms. We'll go ahead and combine and get x squared plus 5x minus 14. So see how we've gone ahead and combined the negative 2x and the positive 7x looks like x squared plus 5x. Awesome. And then we'll go ahead and do the same thing for number 4. Number 4, I'm going to combine them already. And so here we go. X times x is x squared. My outer product then, x times 5 would be plus 5x. When combined with my inner product, negative 9x is going to yield the linear term, negative 4x. Does everybody see that? When we combine that plus 5x and the minus 9x, we get negative 4x. And then minus 45. So this time I skip that middle step in the interest of time. And lastly, I'll throw that middle step back in there now when I have y's mixed in with my binomial x's. So here we go. Ready? X times x is x squared. X times plus 2y is plus 2xy. Negative 3y times x is minus 3xy. And lastly, negative 3y times positive 2y is negative 6y squared. So we want to make sure we're being careful with our rules for multiplying variable expressions. We add exponents when we multiply variables together with the same base. We'll add the exponents. And now we can combine like terms, right? See how this xy term and this xy term have the exact same variable components? It could be yx or xy as long as it's x to the first and y to the first, right? In the same term, then they're going to be like terms. And so we'll go ahead and put my final answer is x squared minus xy minus 6y squared. And we'll go ahead and box that bad boy. Great. What questions do you guys have about today's Bellwork? Okay, so let's go ahead and see all the space that I had to work with and then still skipped it. and take care of our assignment number 2. So this is just the book work. We've gotten stamps for our worksheet number 2. Don't pass that in, right? You're going to keep that as part of our stamp count. So you're not passing in the worksheet. This is just for the book work. And our book assignment then, number 2, was out of 11. Give yourself credit for those you completed out of 11, please. Divide, enter, multiply by 4, and if you showed me your reading question 11.3 on the way around this morning, you'll be able to add that additional point. Box here in the campus, score round to the nearest half point 0.05. Now I'll go ahead and pause the recording while we check our answers then. Okay, ladies and gentlemen, let's go ahead and take a look at our content objectives for the day. Today we're going to be factoring polynomials, and so factoring is undoing the multiplication like we did with the polynomials in Bellwork. Factoring is undoing multiplication, and that's what we're going to do today. We're going to specifically focus on factoring, right, trinomials when the leading coefficient is 1, so each of the answers in your Bellwork would be a candidate for today's factoring. We're also going to look at special patterns, right, which is just taking a binomial and squaring it, or taking the same entries in a binomial but opposite operations. So we'll look at and see examples of each of these forms today. Firstly, I want you to know that factoring a polynomial is simply rewriting that polynomial as a product, right? That is a multiplication of smaller degree polynomials. Or we undo the multiplication that we did for Bellwork today already. If we think about a polynomial, 2x cubed plus 4x squared, that could come from a product of two smaller polynomials, that is lesser degree polynomials. If we undid that multiplication, we could see that, oh, present in each of those terms is a 2x squared hiding. 2x squared is a factor of each of those terms. If we were to factor out this 2x squared from each term and multiply it through this lesser degree of polynomial, x plus 2, do we see we get the original result in blue? Let's go ahead and take a look. What's 2x squared times x? Well, that's 2x cubed. Plus, what's 2x squared times 2? Well, that's 4x squared. And so by rewriting that first one, right, as a product of lesser degree polynomials, that's factoring the original polynomial. And now we're not learning how to do this right on this slide. We're just showing you some things that it looks like. The second kind we're going to deal with is trinomials. That is a 3-term polynomial with a leading coefficient of 1. Like the second one, 1x squared plus 3x plus 2. We're going to figure out how we can go backwards and rewrite that as a product of two binomials like we started with in our Bellwork problems today. So that's going to be the second focus of today's class period. But first, let's go ahead and think about what it means to be a factor of a given term. So let's list all the factors of 9x squared. Everybody on your note sheet? Let's consider the factors of 9x squared. Remember, to be a factor of something, it just means that we can divide evenly into it, right, for us without a remainder. And so 9x squared, we think about all the things that would divide evenly into 9x squared without a remainder. And there's a whole slew of them. Plus and minus, we'll just say for positive or negative 1. Of course, would divide evenly into it. 3 would divide evenly into it. 9 would divide evenly into it without a remainder. All of those would divide evenly into 9x squared without a remainder. But that's not all. X would also divide evenly into it. 3x, 9x. Those are all factors of 9x squared because they divide evenly into 9x squared without a remainder. Oh, but that's not all. X squared, 3x squared, and 9x squared. All of these, right, all of these are factors of 9x squared. And so when we talk about factoring, what we want to do is rewrite it in simplest form, so we're always going to pick the greatest common factor. The greatest common factor. So we now consider number 2. What's the greatest common factor between the two terms 2x to the 4th and 10x squared? We're looking for the largest factor that appears in both. And what's common to each of those terms? Well, they're each divisible by 2. Does everybody see that? They're each divisible by 2. The second one's divisible by 5. Is the first one divisible by 5? No. So the greatest common factor, the numerical portion of the greatest common factor, would just be the 2 because they're both equal. And then they each have x's in them. How many x's do they have in them? Well, the first one has 4 x's. The second one has 2 x's. And so the greatest common factor that's shared by each of them would be an x squared. I couldn't factor out an x to the 4th because the second term only has 2 x's. It only has an x squared. Therefore, the greatest common factor between those two terms is 2x squared. Let's consider number 3. The greatest common factor between each of these 3 terms, right, must be shared by all of them. That is, must divide evenly into each of them without a remainder. So it looks to me like 5 goes into each of these, yes, so 5. And they all have x's. How many x's do they share? Well, each one has 2 x's at minimum. And then, oh, can we factor out a y? No, only the third term has y's in it. The first 2 terms do not have y's in it, therefore y is not common to each of the terms, so my greatest common factor is just 5x squared. We could think of factoring polynomials of this type, greatest common factor, as a reverse distributive property problem. So 4 times what equals 12x? Well, that's easy. 4 times 3x equals 12x. Plus 4 times what equals 20? Well, 4 times 5 equals 20. And so another way to rewrite 12x plus 20 in factored form would be to factor out of 4, the greatest common factor from each term, and then write the remaining terms, right? After dividing out that 4, we have 3x plus 5 remaining. And we can always check by doing a distributive property problem. What's 4 times 3x? Oh, 12x. Plus, what's 4 times 5? Oh, 20. Next, what's the greatest common factor present in each of those terms? Well, it looks like they all have n cubed. And so if we were to factor out an n cubed, what terms would remain in a reverse distributive property problem? So here we go. N cubed times 3n would be 3n to the 4th in the original. Minus n cubed times what equals 5n cubed? Well, just 5. And so by factoring out an n cubed, we could rewrite that in a reverse distributive property problem. And we could always check with multiplication. All right, if we were to factor out a 3, that is, divide out a 3 from each of those terms, we could see what remains in this 3-term polynomial. Go ahead and do number 6 with your partner. Divide out a 3 from each of those terms and see what will be remaining in that reverse distributive property problem. Be ready to share with the class when I call on you. So divide out a 3 from each and see what remains. Okay, so what do you guys have left in the parentheses then? Adam and Heather?
2 squared equals 4y.
So 2y squared minus 4y and then plus 7. Nice job. Raise your hand if you have the same thing in green. 2y squared minus 4y plus 7. Good. 3 has been factored out of each term, and that's what's remains in green. Good job. And lastly, a 4a squared b factored out of each term. That would be 4a squared b times 1 would give me the first term, plus 4a squared b times 4. We need one more a, and we need one more b. So it looks like 1 plus 4ab would be what remains. That would get me to 4a squared b plus 16a cubed b squared. Awesome. Does everybody see it? So we're just doing a reverse distributive property problem. It's a reverse multiplication problem. That's what factoring is. It's undoing multiplication. Awesome. So let's go ahead and use the distributive property to factor out the greatest common factor. With your partner, go ahead and rewrite 3x squared plus 6x as a distributive property problem. So we want to stop, think, GCF. All right? Stop, think, greatest common factor. Is there a greatest common factor hiding in each of those terms that I could factor out in a reverse distributive property problem? Absolutely. What's common to each of those terms? Right? What's common to each of those terms? Tyler?
3x.
3x, right, is the greatest common factor because each term is divisible by 3, and each term has at least one x in it. So 3x is my greatest common factor. Good job. Times. And now after factoring out a 3x from each of those terms, I would have what remaining? Well, 3x times x would give me the first term, 3x squared, plus 3x times what equals 6x? 2. It's that easy. And so we're going to factor out the greatest common factor and rewrite it as a distributive property problem. Your remaining polynomial in parentheses will always have the same number of terms as your original when doing a greatest common factor problem. When doing a GCF problem, your parentheses polynomial is always going to have the same number of terms as your original. So if there's 2 terms in the original, then we'll have 2 terms remaining in my parentheses polynomial. Awesome. So let's go ahead and take a look at the second one. negative 4x cubed y squared plus 16x squared y minus 20x to the fifth. Goodness. So it looks like we'll scan the problem. We'll see what's common to each of those. Well, there's a, let's see, there's a 4 in each term. So I think 4 is the greatest numerical factor. There's x's in each term. So the minimum number of x's in each term is 2. So we can get x squared. And then we can't factor out a y because the third term doesn't contain a y. And so we can't factor out a y, my greatest common factor. If the leading coefficient is negative, then I like to factor out a negative so that my remaining polynomial, right, has a positive. So what I'm going to do is I'm going to factor out negative 4x squared. Does everybody see that? I'm going to factor out a negative 4x squared. In that way, we've gotten a 4 out and an x squared from everybody. I chose to take the negative out, so I'm not confused about this operation here. I want it to look like multiplication. I don't want anybody to think it's subtraction. So I'm going to factor out a negative along with it. What remains then? Well, negative 4x squared times what equals negative 4x cubed y. Well, I need one more x, and I need y squared. Right? Don't I need 2 y's? Then negative 4 times negative 4 gets me the 16. I already have my x squareds, but I need a y. And we're one term to go, guys. Negative times positive equals the negative 20. So positive what? 5. And we need how many more x's? How many more x's do we need? 3. So x cubed. And I think we've got it all. So there we go. We've got negative 4x squared. Let's go ahead and check. Times xy squared would give me negative 4x cubed y squared plus 16x squared y minus 20x to the 5. Is that what I had for the original? Yes. Math works. So a greatest common factor problem, we're finding the greatest common factor, right, present in each term, and then rewriting it as a distributed property problem, and you can always check your answers. What questions do you have about our GCF? Greatest common factor. All right. Another way to think about factoring out a GCF is division, right? Factoring is undoing multiplication. So what undoes multiplication? Well, division does. If we wanted to factor 4w squared plus 192w to the 7th, the greatest common factor present in each is 48w squared. If we were to factor out a 48w squared, we could think about it, the remaining polynomial, as containing the terms when we divide that original by 48w squared, each one. So we could break that up as 48w squared divided by 48w squared plus 192w to the 7th divided by 48w squared. And now simplify each one. So what's 48w squared divided by 48w squared? That's just 1. Plus, what's 192w to the 7th divided by 48w squared? Well, here it looks like 48 is going to go into 192 1, 2, 3, 4 times, because 4 times 50 is 200. So 4 times 48 would be 8 less than 200 is 192. So that looks like 4. And then w to the 7th divided by w to the 2nd is w to the 7th minus 2 is 4w to the 5th. So 48w squared times quantity 1 plus 4w to the 5th would equal my original numerator. We can do the same thing on the other side. Again, we'll just break that up into two separate fractions and simplify. I'll go right to the answer in the interest of time. So 21 p to the 4th q cubed divided by negative 7 p cubed q is going to be negative 3 p q. Minus divided by minus is going to be a positive. 35 over 7 is going to be 5 p to the, looks like 3rd, and then no more q's because q divided by q is 1. So you can think about factoring as division, if that's helpful for you. Okay, but What I'm really excited about, right, is making sure that you're able to do this on your own. So we want to go ahead and stop, think GCF, go ahead and decide, do these with your partner, okay, do these with your partner, go ahead and factor out the greatest common factor, and then in parentheses, what remains is those terms divided by whatever your GCF is. So go ahead and do a 10 through 13 and stop. So go to 10 through 13 with your partner and then stop, and then we'll check together. Okay, let's go ahead and check and see how we do with our GCF, our greatest common factor. So here we go for the first one. Go ahead and tell us the factored form for number 10. All right, what's that going to look like? Ben C.
For 10?
Yep.
3x minus 7, like 5.
Oh, great. So let's go ahead and put that greatest common factor, right? Let's put that up front. And so this would equal 5 times 3x minus 7. Absolutely right. Good job. So raise your hand if you had 5 times 3x minus 7. Who had that? Good job, you guys. And so we'll go ahead and put that greatest common factor out front, and then we'll rewrite the remaining polynomial in parentheses, and we can check by distributing. So 5 times 3x is 15x. Minus 5 times 7 is 35. And so we see that that is, in fact, correct. Good job. In number 11, you want to make sure that you grab the x2. And so some people were just grabbing the 8. You want to make sure that you grab 8x as your greatest common factor. Not just a common factor, but the greatest common factor. So make sure you grab an x2. And then that would leave you with, right, 3x minus 1. Raise your hand if you had number 11 already. So go ahead, 8x times quantity 3x minus 1. Good job, you guys. Number 12 could be rewritten first. Notice how 20 and 2 are like terms, so you could combine that. You could combine that as 22 minus 6x first if you wanted to. And that would result in an easier factorization. Otherwise, you could combine like terms in the parentheses at the end. But we want fully factored form. So what's the greatest common factor? Looks like they each have a 2. Then that would be 11 minus 3x, because 2 times quantity 11 minus 3x equals 22 minus 6x. And lastly, stop. Think. GCF. What's the greatest common factor hiding between these two terms? Well, it looks like a to the 4th is it. So a to the 4th is the greatest common factor. What would be remaining? 18 minus ax. We could always check with the distributive property. A to the 4th times 18 is 18a to the 4th. Minus a to the 4th times ax is a to the 5th x. And there it is. And so we can check our answer every single time. And that's the nice thing about these problems. What questions do you guys have on 10 through 13? All right. So my favorite kind is factoring a trinomial, right, into a product of two binomials. I love this day. I love next class period because factoring, right? Factoring is like a little puzzle. You're going to figure out those pieces, those binomial pieces, like your Bellwork questions, from whence the multiplication came. So it's like undoing the multiplication, and we get do a puzzle every single time. So I really like factoring. It's one of my favorite things to do in advanced algebra. All right, let's go ahead and consider our general strategy. So when we're factoring a trinomial with leading coefficient of 1, oftentimes it factors into a product of two binomials. We're going to go ahead and use our Bellwork pattern, our Bellwork problems, to kind of set the stage for undoing these. When we multiply two binomials together that have the same sign, the resulting terms are all, right, I'm sorry, we're both positive, the resulting terms are all positive. If we had two binomials that multiplied together where the middle term was both subtraction, right, the middle term was both subtraction, then my middle term was negative, and I still had a positive constant. And then if I had opposite signs, then the result was harder to see. My constant term was negative. That's going to kind of drive our factoring process, and we'll see what that looks like in just a minute. Lastly, we're going to go ahead and determine, right, the factors of that constant term C, then multiply to give me the constant term, but sum to give me that middle term, that B. So this looks kind of complicated. Let's go ahead and take a look at some tangible examples and do them together. So the first thing we'll do is we'll take a look at our trinomial and we'll list the factors of the constant term. So everybody, let's go ahead and find x squared minus 12x plus 20. Everybody find the constant term. The constant term, right, the constant term is that plus 20. I'm going to go ahead and list the factors of that 20, and I'll always do plus and minus because sometimes we'll have both negative, sometimes we'll have both positive, sometimes we'll have one or the other. So what I'm going to do is I'm going to do plus or minus 1, and 20 is one pair. But that's not the only factors, the only pair of factors. 1 times 20 is 20, but so is 2 times 10. So another pair of factors is 2 and 10. What other pair of factors multiplies to give me 20? Margo? 4 and 5. So I've got 1 and 20, 2 and 10, and 4 and 5. Those are my pairs of factors, right, that would multiply to give me 20. Anything else? Well, 5 and 4 is already contained in the 4 and 5, so I'm not going to list any more. Right? I'm not going to list 10 and 2 and 20 and 1. They're already contained here. All right, now I'm going to go ahead and use the numbers from my factor list, and I'm going to find the right pair, which will sum to give me the middle term. So ready? Let's go ahead and make my product of two binomials. We'll fill in our variable. I know that my first must have been x and x for my Bellwork. That's the only way to multiply together. X times x gives me the x squared. Now I'll consider my signs in the original. My constant term 20 was a positive 20. A positive 20. And so the only way to multiply two factors together and have a positive result is if they are the same signs. That means my entries here, my binomial, have to either be both positive or both negative. Right? So I need to choose the pair of factors, 1 and 20, 2 and 10, 4 and 5, such that same sign multiply to give me positive 20, but sum to give me negative 12. Which pair of these factors, same sign, is going to sum to give me negative 12? What? Well, do 1 and 20 sum to give me negative 12? No. Do 4 and 5 sum to give me negative 12? No. Only this middle pair of factors, 2 and 10, would sum to give me negative 12, and only if they were each what sign? Negative. And so I need to choose the pair of factors, then multiply to give me the constant term, in this case positive 20, but sum to give me the middle term, in this case negative 12. So what is it going to have to be? It's going to have to be minus 2 and minus 10. What? Let's go ahead and check. My first x times x would be x squared. My outer product would be x times negative 10 is minus 10x. My inner product would be negative 2 times x is minus 2x. And my last would be negative 2 times negative 10 is plus 20. By golly, that does work out. Look at my middle terms. Negative 10x minus 2x gives me that original negative 12x. And that's how I know that I'm correct. So once again, we're going to list the factors of the last constant term. We're going to consider the signs of the constant term. and then choose the pair of factors that multiply to give me the constant term, but sum to give me the middle term. So -2 and -10 sums to give me the -12. Let's try another one. X squared minus 5x plus 6. So we'll go ahead and make my parentheses. Fill in my variable. And then list the factors of the constant term. What pairs of factors multiply to give me 6? Well, plus and minus 1 and 6, but also 2 and 3. So we'll list the pairs of factors for the constant term. 1 and 6 and 2 and 3. Which pair of factors, 1 and 6 or 2 and 3, multiply together to give me positive 6, but sum, that is add together to give me my middle term, -5? What? Well, what sums to give me -5? In this case, we've got two options. Right? Can I get to -5 using 1 and 6? I could, right, with a positive 1 and a -6, that would sum to -5. However, if I multiplied -6 times positive 1, the result would be -6 for my last term. Did I have -6? No, I had positive 6, which means that my factors have to be same sign. The only way to multiply together and get that last term positive is if they're both positive or both negative. For us, are they both going to be positive or both going to be negative if my middle term was negative? They're going to have to both be negative, so I can even fill that in. So which pair of factors will work here? Well, they multiply to give me positive 6, and they sum to give me -5. It better be -2 and -3. Notice how they multiply together to give me a positive 6, but they sum together to give me a -2 minus 3x is minus 5x. Does everybody see that? So we need to be able to, right? We need to be able to think about multiplication and addition in my choice of factor selection. Let's try another one. Number 2, we'll go ahead and make my parentheses. Fill in my variable. And then consider my pairs of factors for the last. And in this case, I have a -24. And so we'll see how that affects my choices for my placement of my factors. Here we go. What pairs of numbers multiply to give me 24? Oh gosh, a whole slew. So I've got plus and minus 1 and 24. All right, what's another pairing? Logan?
8 and 3.
8 and 3, good. What's another pairing? Another pairing. Aaron?
4 and 6.
4 and 6, good. Are there any more hiding out there? Adam? 2 and 12, great. I think we've got them all. So we've got 1 and 24, 2 and 12, 4 and 6, and 8 and 3. Now, we need to find the pair of factors that multiplies to give me -24, but sums to give me -2. And so we've got lots of choices here. However, the fact that my last term is negative means that my entries have to be opposite signs. The only way I can multiply two terms together and get a negative result, a negative product, is if they're opposite signs, one positive and one negative. So we can use that to our advantage. I'm going to go ahead and fill in one positive and one negative. That'll help me with my selection. Now, which of these pairs, one positive and one negative, multiplies to give me the -24, but sums to give me the -2x? Raise your hand when you found it. So which of those I'm going to have to use? Right? They sum to give me the -2x. What's it going to have to be? Cody?
4 and 6.
4 and 6, absolutely. Which one positive, which one negative? If they sum to give me a -2x, then the larger one better be negative, which means I'm going to put exactly what Cody said, a +4 and a -6. Everybody look. X plus 4 times x minus 6, the positive 4 times the -6 gives me the -24, but the positive 4 and the -6 sums to give me the -2. So it has to be the negative with the 6. Now you could have put x minus 6 in parentheses times x plus 4 in parentheses. That's correct, right? But the negative has to go with the 6 and the positive has to go with the 4. Awesome work. Great job, you guys. All right, go ahead and try 3 then, and 4 by selecting the pair of factors of the last term, the constant term, that multiplies to give you the last, but sums to give you the middle. So go ahead, I'm going to walk around, and if you have a question, right, just go ahead and catch my eye. We'll make our parentheses. And with your partner, go ahead and decide which pair of factors you're going to have to choose. Great work, you guys. Okay, go ahead and share your answer for number 3. You can go all the way to the answer. So what did you get for number 3? X squared plus 8x plus 15 is a product of two binomials. What are those binomials? Caitlin T? Plus 3 and plus 5, either order because they're both positive. Who had x plus 3 times quantity x plus 5? X plus 3 times quantity x plus 5, or x plus 5 times quantity x plus 3 is the same thing. Good job, you guys. Notice how Caitlin's factors, positive 3 and positive 5, multiply to give me positive 15 and sum to give me positive 8. And so positive constant means same sign. Given that they're same sign factors and the middle term is also positive, they must both be positive. And then we select the pairing that sums to give me the 8. Absolutely. Great job. Let's go ahead and take a look at the next one. This is a little bit trickier because of the negative 18. The negative 18 here means that my entries, right, are going to be opposite signs instead of same sign. That's trickier. What did you get for your final answer? Your final answer for that one? Carson S?
Negative 3 and positive 6.
Negative 3 and positive 6. Raise your hand if you had x minus 3 times x plus 6 or x plus 6 times x minus 3. Either order is fine so long as the negative goes with the 3 and the positive goes with 6. Way to go. That's perfect, Carson. Thank you. Guys, either order is fine for your parentheses, but the negative has to go with the 3 and the positive has to go with the 6. How come? Well, if you multiply this out, we need the larger factor to be the positive, so that when you sum the outer and inner product together, you get the positive 3. So you need the larger number to be with the positive in order for that middle term to be positive. Let's try. X times x is x squared. X times plus 6 is plus 6x. Negative 3 times x is minus 3x. And negative 3 times 6 is minus 18. So in this way we can see, by golly, we would get a plus 3x from our middle term when I combine like terms. Way to go. Good job, you guys. I'll go ahead and box that. And we continue. But first, what kinds of questions do you have on 1 through 4? All right. Last thing we're going to do is to consider, right, some of these special patterns. And so when we take a binomial and multiply it by itself, that is a binomial squared, the result is always a trinomial. If we took two binomials that had the same entries but the opposite signs, then that's when we got the special patterns when we just got a 2-term. And so it's easy to match up what these look like. The first one, the second one, or the third one, based on an original trinomial. Notice how the first polynomial, 9x squared minus 1, just has 2 terms. It's a binomial, so that must be a special product. It must be the first term. That is same entry, but opposite operation. So what times itself equals 9x squared? Well, 3x times 3x equals 9x squared. What times itself equals 1? Well, 1 times 1 equals 1. And lastly, what must my signs be so that the outer and inner product are exact opposites and cancel each other out? So there's no middle term. Well, they must be opposite signs. And so one positive and one negative, either order. Right? It could be minus and then plus, so long as they're same entries, opposite operations. Everybody see that? So they're the same entries, opposite operations. Let's try the second one. X squared plus 10x plus 25. Which of these patterns does that most closely resemble? The first one, the second one, or the third one? Which of those does it most closely resemble? Braden? The second one. They're all positive, so it must come from a binomial times itself with same sign. And so what must that come from? Well, it must come from what times itself equals x squared? Well, that must be x and x. What times itself must equal 25? Well, that must be 5 and 5. And we've got same sign, both positive, so it must be plus and plus. How do we get the 10x? Well, if we multiply that out, we get x squared plus 5x plus 5x. That combines to give me the plus 10x and the plus 25. You might see this written on your worksheet as x plus 5 quantity squared, just like that. And that's fine. Right? You could also leave it like this and get full credit. Again, I would agree that the second pattern most closely matches the third one because it's plus plus. And so that must be the second one. Let's do that one. P times P is P squared. What times itself is 16Q squared? Well, 4Q times 4Q is 16Q squared. And then it looks like same signs, both positive. So plus and plus. X squared minus 121, what times itself equals x squared? Well, x and x. What times itself equals 121? Well, 11 and 11. And lastly, what must my signs be, right? What must my signs be so that there's no middle term? I need my outer and inner product to be exact opposites and cancel one another out so that there's no middle term remaining. Well, they must be opposite signs. So I need one positive and one negative, either order. All right, go ahead and try the last two with your partner. Be ready to share. So consider the signs. That's going to tell you what you're going to fill in. Positive or negative. Okay, so I asked myself, what times itself equals 16b squared? Oh, that's 4b and 4b. What times itself equals 25a squared? Well, that's 5a and 5a. Now, I consider the signs. My last term was negative. The only way to multiply those two things together and get a negative is if they're same sign or different. They must be different sign. That would ensure the outer product and inner product are exact opposites and sum to 0, meaning there's no middle term there. So we need one positive and one negative. Raise your hand if you had 4b plus 5a times 4b minus 5a, either order with the signs. One positive, one negative. Good job. Go ahead and share your answer then for the last one. What would you have for the last one? X squared minus 14x plus 49. What does that factor into? Luke?
Quantity of x minus 7 squared.
Absolutely. X minus 7 times x minus 7. You could rewrite that as x minus 7 quantity squared, right? And that will show up on your worksheet as well. Or you could leave it as x minus 7 times x minus 7 and get full credit. Raise your hand if you have the same as Luke. X minus 7 times x minus 7. That's right. Good job with the signs. What questions do you have about your special pattern? All right, so we're going to be right on time. We can go ahead and now do some practice. Here we go. I'm always on the lookout for perfect squares. If I see perfect squares on my first or my last, that could be an indication I'm dealing with a special pattern. However, I still can do these just like we did before. I'll make my parentheses, fill in my firsts, consider my pairs of factors for the last, plus or minus 1 and 4 and 2 and 2, and then choose the pair that multiplies to give me 4, but sums to give me negative 4. Well, I can't use 1 and 4 because that would sum to give me 5, right? Or 3. And so I have to use 2 and 2. And it looks like same sign, both negative. What times itself equals 36? Oh, 6 and 6. The last term being positive means same sign. And if the middle term is positive, then they must both be positive. So x squared plus 6x plus 6x would be giving you a 12x and then plus 36. Awesome. What multiplied by itself gives me 144? Well, 12 and 12. My original was a binomial, so I must have opposite signs in the original factors in order to ensure the outer and inner product are exact opposites. And we're one to go. And in this case, it looks like same signs, but both negative. In order to get to negative 6x, we must have negative 3 and negative 3. That would combine to give me my negative 6. That's pretty sweet. And what questions are you having on our special patterns? Special patterns? All right. So we'll go ahead and combine these. More than one strategy is needed. So we always want to start with our first thing, stop, think, GCF. Is there a greatest common factor hiding in each term that I can factor out first in a reverse distributive property problem and then result in smaller numbers and an easier problem? So here we go. Stop, think, GCF. Is there something that's common to each of those terms? Yeah. What do they all contain, Brady?
3.
A 3. So let's factor out a 3 first and rewrite with smaller numbers. So 3 times what equals 3x squared? Well, 3 times x squared plus 9x plus 20. Now we'll go ahead and take a look at that green polynomial. That's a trinomial, which oftentimes factors into a product of 2 binomials. So we've got to keep going. What? We've got to keep going. We'll keep this 3 out front. That's part of the original problem. It's going to be part of the answer. But we'll break up that green trinomial into a product of 2 binomials. What is x squared? Well, x and x. And now we'll factor, right? We'll think about the factors of that last. Everybody, this is the trickiest part, but my favorite part. What are the factors of my constant term, positive 20? Oh, plus and minus 1 and 20. 2 and 10, and 4 and 5. Which pair of factors, 1 and 20, 2 and 10, or 4 and 5, multiply to give me the positive 20, but sum to give me positive 9? Well, that's the key. I need them to sum to give me positive 9. So is it going to be 1 and 20? No. Is it going to be 2 and 10? No. It's going to have to be 4 and 5, both positive. That would sum to give me plus 4 plus 5 is plus 9. Does everybody see that? So it's going to be x plus 4 and x plus 5, either order as long as they're both positive. Awesome. Stop. Think. GCF. Is there a greatest common factor hiding in each of these that we can factor out and make it smaller numbers? Yeah, it looks like everybody's got a 2. Is that it? 2? Darn it. And an x. So let's factor out a 2. X. And now it would leave me with 16x squared minus 24x plus 9. And I better use blue. And what kind of numbers are 16 and 9? What do you recognize about those numbers 16 and 9? Right, what kind of numbers are 69? Logan? They are perfect squares, and so that's an indication that this might be a special pattern. Let's keep going and try. We'll keep our 2x, and we'll say what times itself is 16x squared. Oh, 4x and 4x would result in a first product of 16x squared. What times itself is 9? Well, 3 and 3. And lastly, are these going to be same sign or different? Well, they have to be same sign in order to multiply to give me a positive constant term, but both negative in order to sum to give me that negative middle term. So it must be 4x minus 3 and 4x minus 3. That's pretty sweet. And that's the trickiest kind that we'll have on our day three worksheet. All right. So let's go ahead and choose which response. All right. For each of these, we're going to take 3 minutes with your partner and then come back together and share. And so we can just select your response A, B, or C, or A through F or 2, and 3 and 4 are the key ones. We want to see what relationship exists between M, N, and B versus what relationship exists between M, N, and C for the last one. Okay, let's go ahead and share our responses then with the class when I call on you. Please be ready. When factoring GCF refers to blank, We've got greatest common factor, global currency fund, or Grant County Fair. So a lot of choices here. I'm interested to see which you pick. So what does GCF stand for? What does GCF stand for? Taylor?
A, greatest common factor.
A, greatest common factor, absolutely. A, greatest common factor. Thank you. Number 2, factoring a polynomial, factoring a GCF is similar to blanking a polynomial by a term. And while I'm always hungry regardless of which hour of the day, I don't think it's eating. I don't think it's eating, though polynomials taste good. So factoring a GCF is similar to what? To what? Marina?
B dividing.
B dividing is correct. Raise your hand if you have B dividing. So if you divide out a greatest common factor from each term, that tells you what's remaining in the parentheses. Good job. All right. The key today is factoring. Then what's the relationship between M and N and B? What's the relationship there? Olivia, B?
M plus N equals B.
Perfect. M and N must sum to give me the middle term B. Absolutely right. And Olivia, what's the relationship between M, N, and C?
M times N equals.
Absolutely. When I multiply M times N, then I must get the constant term, that last term, the constant term C. Absolutely. What questions do you guys have about your closure today? Great work. We've got assignment number 3 is worksheet number 3, factoring for next time, and I'll go ahead and save the recording. Nice